This is 3D scanning and mapping of turbine components, a senior Capstone project sponsored by Siemens Energy.
LiDAR, light detection and ranging, has functions in field, aerial, and satellite metric survey.
LiDAR scanners are now an added feature on newer Apple iPhone and iPad models and allow for better accessibility and new development in 3D modeling. Throughout the course of senior design, we developed a mobile LiDAR application to take 3D scans of turbine components for Siemens Energy.
These scans give shape and surface information that offer context to images of components that were previously difficult to tell apart. Before we go into our solution, we'll first introduce ourselves.
Hi, my name is Joe Fioresi, and I worked on the backend database, maintaining the connection between the mobile application and the desktop interface.
Hi, my name is Melody, and I work on the 3D processing portion of this project, as well as the desktop interface that facilitates that processing.
Hello, my name is Jessica Nguyen, and I worked on the mobile application for this project.
Hi everyone, my name is Jennie, and I worked on the mobile application, specifically the front end and the UI and UX design.
Hi, this is Julie. I did research and implementation on the 3D data processing and matching portion of the project.
Siemens provided us these physical components so that we can develop and test our software.
We scanned the physical components and a provided computer-aided design model to see if today's technologies are accurate enough to provide a good mapping.
We completed the following: an iOS application, which then uploaded files to a database, connection to a desktop application, and 3D data processing.
When a field engineer opens up our application, they will be prompted to a login page. For the purpose of this demo, we will be logging in anonymously. Once logged in, we will be prompted to the home page where we could start our scanning session. Once we click start, we will be then prompted to the specification page where we are required to put the component type and the style number. The serial number will be optional. Once the user puts in all the inputs for the specifications, they will click camera to start the image and scanning capture session. The user will have to turn on the camera feed by clicking on the eyeball on the bottom left. The middle button will start the scanning process and simultaneously take the 2D image at that position. The engineer will be able to see the scan data that they have generated by clicking on the eyeball on the bottom left. Once the engineer has created a successful scan, they will then click on the Review Images button. On the Review Images page, the field engineers will be able to review all the 2D images that they have taken during their session. Once the field engineers are satisfied with their captures, they can then upload to the database, where the program can start the processing.
For our backend database connection, we use MongoDB Atlas. We start at our mobile application, where we take information from the user capture session and we post this data to our Atlas database. This is done using MongoDB Realm, which is a mobile database platform that gives us a variety of quality of life features such as online-offline sync, multi-user support, and cache logon information. This is then connected to our desktop app, which is able to get, post, and delete data from our Atlas database, and we make sure to save files to the database in a format that makes them ready for 3D processing. This is an entity relationship diagram describing our database structure. We start at the user, who has a variety of identification fields along with references to each of their individual scanning sessions. We also have the parts, which contain the component's type name along with the ground truth CAD model that the scans are being compared to. Each user scanning session is found in image collection, which stores all of the information related to the user's capture sessions. So they start with the image array and scan array, which has the individual images and scans that the user captures. The images are stored in JPEG format to maintain the EXIF metadata in case the user wants to access it. And then this collection also has a variety of other useful information fields that the user may want to access about the individual scanning session.
After scans have been taken and uploaded, those back in the office can access those scans to begin the processing. Using the component specifications given on the mobile app, a user can select the component type, style number, and the scan. We also present the option to preview your scan, preview the ground truth target, and preview the images. Once ready, the user can click Run to begin processing. The interface first displays a first matching result. In the case of a poor matching result, like this one here, the interface then allows the user to conduct a manual rescaling. Once processing is complete, the interface outputs a results page. Here you can see and preview your image and your scan. Finally, the user can see and view the final output of the algorithm. Here we have the scan mapped onto the ground truth model of this component.
To process the 3D data, we used a clustering algorithm to segment the desired component from the background, and then we recreated some surface information using normal vectors and fast point feature histograms in order to get the local shape data. Once we obtained the shape data, we were able to match the scanned component onto the provided ground truth model using first a global rough alignment and then a closest point refinement.
Over the past 2 semesters, we have worked diligently as a tight-knit team to accomplish the goals of this project and overcome obstacles that we faced. With any project, some of those obstacles took more time to overcome than others.
At times, during testing, our scanned point clouds would capture extraneous artifacts and background clutter, making segmentation difficult. As a workaround, we took closer, focused captures. Additionally, in edge cases where only portions or fractional lengths of the components are scanned, our bounding box resizing method would not perform optimally. We included a user resizing step to circumvent these edge cases. Lastly, our clustering algorithms are sensitive to parameter initialization and random iteration. Future development of a parameter tuning or regression method would be necessary to generalize our approach.
Creation of the application was a complex and challenging process. Tasks and functions that seemed simple to implement wound up being much more troublesome and complicated than we expected. None of us had any experience with iOS development, so learning frameworks and libraries was where the learning curve began. This included SwiftUI, UIKit, ARKit, AVCam, Foundation, Metal, and the list goes on.
Another general difficulty we faced was maintaining good communication among all parties. Our project scope shifted from a computer vision/machine learning architecture to a project involving more mathematical and iterative approaches. After a couple meetings with project sponsors and advisors, it ended up taking longer than we anticipated to finalize what our project really entailed. A new tool we learned of, called a requirements matrix, helped us with this back and forth process, with both Siemens advisors, our weekly advisor, and ourselves. Weekly meetings and correspondence internally amongst ourselves was also key. We found it important to make sure the team sat down together, whether it was in person or online, and discussed plans of actions to ensure we were always on the same page. In the end, this was a tough but rewarding project. We learned many things, not only within the technical scope of this project, but also things like how to effectively work on a team and the importance of communication.
But even though this all proved to be a difficult assignment, we were able to endure through all of it as a team.
We got valuable project experience working with a legitimate stakeholder, teaching us new skills that will directly benefit our futures.
This has truly been a magnificent journey in front-end, back-end, and new technology exploration. We thank you for tuning in.